So what are geostationary satellite? Geostationary satellites are the one which revolves around the Earth at a height h from the surface of the Earth, and it rotates it revolves around with the same angular velocity as the rotation of the Earth, and also goes about in the same direction as the rotation of the Earth about its own axis. The relative velocity Va minus Vp becomes 0 because both of them are the same direction, and that's the reason why a person on the Earth's surface is up. For the person on the Earth's surface, the satellite appears to be stationary, and that's the reason it's called geostationary satellite. So next is what is the percentage increase in the velocity that is required for an orbiting satellite to escape into the outer atmosphere? I mean to get the escape velocity, to move out of gravity. So orbital velocity versus escape velocity, you know the relationship Va is equal to root 2 times Vo. So the percentage increase in the velocity is Ve minus Vo by Ve into 100. Change in velocity by original velocity into 100. So root 2 V0 minus V0 by root 2 into V0, where V0 can be taken out and throughout get cancelled, and do that root 2 minus 1 by root 2 into 100. But that will be the answer. You can calculate and write the answer, of course. Next question is the time period for a geostationary satellite is given to be 24 hours. Then the height at which it's revolving around, height at which the geostationary satellite is revolving around is 6 times Re. So you just add it with original radius of the Earth to find the total distance from the center of the Earth, 7 Re. Okay, we know we are going to definitely use only Kepler's law, because they are given then another unknown satellite with the height has been given 2.5 Re. So add it with Re so that you get the total distance from the center of the Earth. And then they are asking time period of that satellite. So just write Kepler's law and write the ratio. And Re, this is R geo, and that is time period of geostationary satellite the square by time period of the unknown satellite square is equal to the radius of the geostationary satellite, the whole cube. So 7 Re the whole cube by 3.5 Re the whole cube, where Re cube will get cancelled. This will be 2 when cancelled, and 8. So T geo square by T satellite square will become 8. And so T geo has been given to be 24 hours. Okay, so this is 24 square by T satellite square is equal to 8. So this is 24 square. T satellite square therefore is 24 into 24 by an 8. 4 3s are 12, 3 2s are 6, 72. So we get Ts square to be 72 and Ts to be root of 72, and 12, 6 are 72, and instead you can write 4 into 3. Can I write this is also root of 4 into 3s are 89, 2s are 18. So I can take these two out common, which is 2 into 3, which is 6 root 2. So that's the answer. So then they'll give you a multiple choice question, and the question will go like this: a time period of a geostationary satellite is 24 hours at a height 6 Re from the surface of the Earth. The time period of another satellite whose height is at 22.5 Re from the surface of the Earth. You find the time period of the time period of the satellite is what is unknown. So immediately you can apply Kepler's law and do this. What children do forget is to add this Re, because you need to calculate it from the center, the gravitational forces or central forces. All the distances have to be measured from the center. So let's go to next question. And next, one of the questions that had come for another exam is the tides in the sea is primarily because of dash. It's primarily because of the moon's force of attraction, and not sun's. Primarily because moon is closer to the earth than when compared to the sun, and the force is inversely proportional to the distance and distance square. F is equal to G into capital M small m by r square. So then therefore the moon has a greater effect because the distance is less, the force will be more, and moon's effect on the earth's tidal effect, they call it tidal effect, is more. Okay, that's that. And then the next question, the acceleration due to gravity G at the center of the earth, the answer is 0. That was one of the MCQs which had come in many exam. Next is the orbital velocity of the artificial satellite in a circular orbit just above the Earth's surface is V0. For a satellite orbiting in an altitude half the Earth's radius, the orbital velocity is what? Okay, the orbital velocity of artificial satellite in circular orbit just above the surface of the Earth. Which means, can we take height to be negligible? Approximately, just because this is just above the surface of the Earth. H is negligible, so we can take the distance itself as capital R. And for a satellite revolving around at an altitude half the radius, H is equal to R by 2. Altitude, so you need to add it with R to find the distance from the center, which is 3R by 2. That will be the actual distance from the center of the Earth. And if they are asking you the orbital velocity, and they are asking the orbital velocity, the formula for orbital velocity is already this was given as V0 when height is negligible. Now they are asking for this orbital velocity for the second case, which is V0 dash, and the orbital velocity's formula is root of gm by r. In the first case, it's just r. VO is just root of gm by r, because the height is taken as negligible, so the r plus h, the h will get cancelled. And in the second case, which is VO dash, it will be root of gm by 3r by 2. So 2 goes up. And you already know a root of gm by r from the first equation is V0, the initial one. So V over dash is root 2 times root 2, and there's also 3. Okay, so root 2 by root 3 times the original velocity with which it was going. So this was one of the MCQs. Again, I hope you understood the question. The orbital velocity of an artificial satellite in a circular orbit just above the surface of the Earth is V0. For a satellite orbiting at an altitude of half the Earth's radius, the orbital velocity is what? Okay, so that's the next question. So let's continue. And then I'll read out the next question. Consider two satellites S1 and S2. So one satellite S1 and satellite S2 with the period of revolution. Time period of the first satellite is 1 hour. The time period of the second satellite is 8 hours respectively, revolving around the planet in a circular orbit. The ratio of the angular velocity omega 1 to that of the angular velocity of the second satellite omega 2 is the question. And you know that angular velocity is angular displacement by time. So it's 2 pi by capital T1 for the omega 1, and omega 2 is 2 pi by capital T2. And so then therefore if you want to find the ratio, it's omega 1 by omega 2 can be divided. 2 pi get cancelled, become T2 by T1. So basically it becomes 8:1. Okay, so that's this question. So let's go to the next question. I'm reading out the questions for you. You can take it as notes here. So I'll tell you the next question that's in here. Okay. It seems to be quite a difficult question, but let's do it. Let's explore more. The two stars of mass m and 2m at a distance d rotate about their common center of mass. Center of mass will obviously be skewed towards the 2m because it's heavier. So it's going to spin about this in free space, the period of revolution. So it's going to spin like that. There's a mass m and 2m about its center of mass. The whole distance is d. Okay, and you have to find the time period of the revolution for this spinning to happen. Okay, so let's see how this can be done. You have masses and m and 2m. Yeah, so you know that the distance r1 and r2 satisfy. Let's keep this distance as x and this distance as d minus x, or this is r1 and this is d minus r1, however you want to. And so you can say, since it's about center of mass and you know that left moment is equal to right moment, m into r1 is equal to 2m into d minus r1. So on consolidating this, so let's do m into r1. M and m directly get cancelled, so that's good. r1 is equal to 2d minus 2r1, and 3r1 is equal to 2d. And therefore r1 is equal to 2 by 3 of d. You get it like this, the relation between r1. So if r1 is 2 by 3 of d, this will be obviously 1 by 3 of d, so that this distance, so therefore the total adds up to d. So then, but you know that if it's going to left, the left moment should be equal to right moment, and also what else we can say? The centripetal force of both of these has to cancel out, because it's going to be spinning. It's going to be spinning like this. The m and 2m are going to be spinning like this. There'll be the two centripetal forces which can be say equated. So no, I'm just trying to think. There'll be a force of attraction between 2m and m. Definitely there'll be force of attraction between 2m and m, and that value is g into m into 2m by d square. And that force of attraction between the two, they are actually not coming closer together. Why? Because they're countered by say a centripetal force. That's the reason they are not getting closer together, because of attractive force. So the attractive force is basically countered by a centripetal force, which will be, let's say, centripetal force is mv square by r. Let's take one centripetal force, which is for the mass, first mass, and we can also say, right, mr omega square. mr omega square. So m is the mass of the first body, r is 2 by 3 of d for the first body, mr omega square. And you don't know what is omega square. That's the whole point of this question. Small m and small m get cancelled. And so what is omega square? You get a formula which is 3g 3 to 6. What about this 2? What about this 2? It's m into 2m. Omega square 2d by 3. You will have one more m, and there's one more 2 there. Yeah, and the 2 and 2 also can get cancelled. Can you see? Yeah. So you're left with the 3g small m by d cube with the square root if you take this, and this will be the angular velocity. It's a very, very beautiful sum. Where, what is the question? The question is about a mass m and a 2m are spinning about its center of mass. Find the angular velocity. So take it as r1 and d minus r1 or whatever. And the left moment is equal to right moment. So you get to where exactly the r1, what is the value of r1. And then there is definitely a force of attraction between the two masses, which can be equated to centripetal force of only one of the masses, because this point is going to act like a center of the spinning. The centripetal force is only acting towards the center. So you ideally must take only one of the mass of centripetal force and then equate it and get the value of omega. I hope you're clear. You could have also used 2m. Instead of m, you could have also used 2m. But in that case, the distance will be 1 by 3 into d into omega square. It's the same attractive force, and so you can still get the same answer. So that's an eye-opener. Hope you're all clear with this question. Okay, so you understood the question also very well. So let's go to next. So I'll do some more questions. So the 9th question, I'll read out the question for you. Okay, some other question. The radius of the Earth is 6.4 into 10 to the power 6 meter. What is the minimum speed of the satellite to place it in the Earth's orbit? What is the minimum speed of the satellite to place it in Earth's orbit? So orbital velocity is what they are asking. So we know the formula for orbital velocity is root of gm by r plus h. Okay, what is height? Have they given the h? Let me read the question once again. The radius of the Earth is 6.4 10 to the power 6. What is the minimum speed of the satellite to place in Earth's orbit? They didn't specify, so h can be in that case taken as negligible. So therefore the formula is root of gm by capital R, and you know capital G and capital M. You can substitute those respective values, which is root of capital G is 6.6 into 10 to the power minus 11 into capital M is 6 into 10 to the power 24, which is the mass of the Earth, by on R is 6.4 into 10 to the power 6 or 6 into 10 to the power 6, whatever you can remember. Hence the correct answer will be 7.9 into 10 to the power 3 meter per second. Okay, so that's what is the orbital velocity, and that calculation is also done. I hope you understood that question. So let's go to the next question. The time period of a simple pendulum inside a satellite orbiting the Earth will be. Okay, that's another question. Time period of a pendulum inside a satellite orbiting the Earth. So let's study this point. You know, time period is generally 2 pi into root of L by G, and G itself is 0 meter per second square. When I substitute 0 here, you get time to be infinity. So the time period of a pendulum inside a satellite orbiting the Earth will be 0. Since there is no gravity inside the satellite orbiting around the Sun, you can substitute G as 0 and the time period will get to infinity. This is one of the MCQs in an exam. So let's go to the next question. It's the 11th question. The time period of the artificial satellite in a circular orbit of radius r is 4 days. Time period of an artificial satellite is 4 days. If a time period of another satellite is taking 32 days, the radius of the orbit is. Time period of an artificial satellite in a circular orbit of radius r. For this case, the radius was equal to r. And what is this radius is the question. Radius of the artificial satellite, this is the radius of the unknown satellite. So again, I'm only thinking of using Kepler's law, and Should I use Kepler's law? T square is proportional to R cube. Let's try this sum. I'm going to try this sum and see if I'm getting the answer once again. Yeah, that's all. Directly Kepler's law. You just know that T artificial circulate the whole square by T of the unknown circulate the whole square is equal to the which is nothing but 4 into 4 by 32 into 32 will be equal to the radius of the earth, the artificial circulate the whole cube by radius of the unknown circulate the whole cube, and radius this itself can be taken as r cube. They've given it in the question. So then therefore this is 16 2s are 32, and this rs cube is equal to 64 r cube. So rs is 4 r cube, 4r. It's 4 times the radius of the artificial circulate will be the radius of the unknown circulate. So such questions, very interesting. So I've done so many sums. Let me see if I get more questions in this. So I think I'm done. Okay, let me also do some textbook questions along with this. Okay, so NCERT book back. Hope it's recording. Yeah. So let's go to NCERT book back questions. The first question, I've already discussed this in class. Electrostatic shielding is possible. You can protect yourself from lightning by sitting inside a metal cavity such as car, which provides you an electrostatic shielding, but gravitational shielding is not possible. Gravitational shielding is never possible. Okay, gravitational shielding not possible. So let's go to next. Even if you sit inside the car, the gravity will pull you down towards the center of the earth. So next is there's a part A, and that's part B question. An astronaut inside a small spaceship orbiting around the earth cannot detect gravity. You know, spaceship inside which there's no gravity, we all know that. But if the space station is really, really large, we can hope to detect gravity because it's so huge that it can have its own gravity. If the spaceship orbiting around the earth is large enough, the astronaut inside the spaceship can detect a variation in gravity, because there will be its own gravity will play a role. Okay, let's go to option C. Sum number C. If you compare the gravitational force of the earth due to sun to that of the moon, you will find the sun's pull to be greater than the moon's pull. However, okay, why? Because the pull is capital G into capital M and small m by r square, and the sun's mass is much heavier when compared to moon. Sun versus moon. Okay, moon's mass is lesser, sun's mass is too heavy. So the gravity of definitely this will be greater, the pull towards the sun. But however, the tidal effect is more only for the moon, because when it comes to tidal effect, we should talk about distance, and the distance between the moon and the earth is very less. Moon and the earth is very less, and the force is inversely proportional to distance. So moon's effect on tidal is greater than the sun's effect. One second, somebody is. Is it recording? Yeah. So that explains that the moon's effect on tidal is greater than the sun's effect on the tidal effect is greater due to the moon than the sun. So let's go to next question. Is the second question in the book back. Acceleration due to gravity increases or decreases with altitude. As you go high also it decreases. Height increases also, gravity decreases. Depth increases also, gravity is decreasing. And next part is the second part of the question. And due to depth, that is also answered. Oh, that's the second part of the question, it's already answered. Third question. The effect of rotation on effective value of acceleration due to gravity is greatest at the equator or at the poles. Okay, this is the earth, and the poles is the effect at the poles is greater. Gravity at the pole is greater than the gravity at the equator. Let's see, gravity at the pole is inversely proportional to Rp. Gravity at the equator is inversely proportional to radius of Re. And so, Rp is lesser, so gravity at the pole is definitely greater than gravity at the equator, because radius of the equator is bigger. The gravity at the equator will be lesser. So, we can say that the effect of gravity is greater at the poles. So, that answers the next question. The fourth subdivision. The acceleration due to gravity is independent of the mass. Yeah, small g is capital Gm by r square. Therefore, it only depends on the bigger body, the acceleration due to gravity, say for the earth, and not on the mass of the body. Small m is not there. So let's go to next, which is the fifth formula. You always take g minus g capital M small m into 1 by r2 minus 1 by r1 and to calculate the gravitational potential energy. And we don't prefer to use the formula mgr2 minus mgr1. That is mgh is the potential energy, and using that you can't do this because the small g varies from place to place and height to height. So then the best formula to use is only this and not this. So that's the explanation for the next question. So let's go to next. Next is what is the next question? Third subdivision also zone 1. Then next is third question. Suppose there existed a planet that went around the sun twice as fast as the earth. The planet is going twice as fast as the earth. Means don't write 2 times t. It's going twice, which means going faster. The time will be lesser. In the case of time alone, you have to be very careful in writing this. And so then therefore, what would be the orbital size as compared to that of the earth? Orbital size, Kepler's law is what you're going to use. Tp square by Te square will be equal to Rp cube by Re cube. And Tp itself is 1 by 4 of Te square by Te square is equal to Rp cube by Re cube. Radius of the earth Re is nothing but 1 astronomical unit around the sun. So 1 astronomical unit, and so you can just cross multiply and get Rp cube is equal to 1 astronomical unit into 1 by 4. And taking that side will become whole to the power